today. I would like to introduce you to Etienne Artigau. Etienne was a student with me when I was your age at Université in Quebec. So he did his undergrad together with me. I think you were like 2 years younger than me or something like that, something in those lines. But for his graduate studies, he decided to go at Université de Montreal. Etienne was the very first person who introduced me to the possibility of life in the solar system, like in places like Europa. I remember you introduced me to Europa. You probably don't remember that, but you were already passionate about life elsewhere and the possibility of other things. And you were talking about brown dwarfs and all of that. You were the first person to talk to me about brown dwarfs.
You'll hear about brown dwarfs again.
Nice. He's still passionate about that. So even
they're still around, you know.
Even as an undergrad, he was already passionate about all of that. So at the Université de Montreal, he got involved in the group, the instrumentation group, and got into building an infrared imager, right, for Observatoire du Mont Mégantic, which was a small observatory in Quebec. So that's how he got involved and got his expertise in building instruments in infrared. And then after getting his PhD at Université de Montréal, he went for 3 years at Gemini, I think so.
Yep.
Was it with the Gemini Fellowship?
Yeah, a science fellow. Mm-hmm.
Okay, so he was a Gemini Fellow in Chile. So a nice place to be in the life of an astronomer. And then he got back to Montreal, to Université de Montréal, as he's been since then as a researcher in the IREX group, so that's the Institute for Research of Exoplanets. So he's very involved into getting to know exoplanets and brown dwarfs with infrared astronomy. So he's going to talk about some of his one of his data, like SPIRO, he was building at Université de Montréal. He's also involved in building one of the instruments that's going to be launched in a month on board the James Webb Space Telescope. So he's been around, he knows his stuff. So please welcome Etienne Artigau.
The first thing I want to say is that when you start your master, and hopefully some of you will want to go to grad studies, that there's always a point when you think you know computers because you've seen many Windows computers, and then you arrive with you have a Unix station in front of you, and you're totally clueless. And hopefully there's a friendly grad student that knows around and say, okay, you want to log in, it's here. You want to know where your files are, it's there. And Anne was that friendly grad student that showed me around when I was totally clueless and thought I knew computers. So thanks again for that long time ago. Anyway, let's get started. So you hear, wait. You hear me reasonably well?
Yeah.
Okay. So I'll be talking about SPIRO and exoplanets, as Anne mentioned in the introduction, life, a little bit, and everything else about the project, and a little bit the adventure of building an instrument and getting it from a concept to basically a working machine that produces nice science. So just for some background, I work at University of Montreal. I'm part of the IREX, Institute for Research on Exoplanets. It's a bilingual acronym because we're in Quebec. It's Institut de Recherche sur les Exoplanètes. And the director is René Doyon. It links 4 universities, UDM, where I am, McGill, that you may know, Bishops, where we have Jason Rowe, one researcher, and Laval, that does a lot of optical design. And you'll see that optical design is necessary when you want to build nice instruments. As 9 profs, research staff, and in that research staff, we have more than 25 grad students, summer interns. We have some private funds, private donors, which is always great. There's less of a culture of private funds in the university in Canada. So it's more of a challenge, I think, than historically that has been in the US. We have, and that's a big luxury for a research group, 2 people that are in charge of public outreach. And that's really nice when, well, just to be present in social media and so on, because astronomers are not necessarily good at that in general. So we have people that are dedicated to that, and we're really involved into space and ground-based instrumentation. One of the main instrument is JWST, the James Webb Space Telescope. I won't talk much. I'll briefly mention it because I'll be talking about SPIRO, so a ground-based instrument that's producing exciting science. So before we start, I'll give some background on exoplanets. I don't know if you've seen exoplanets in your Astro 101 courses. But yeah, someone giving a presentation should never underestimate the pleasure of hearing something they already know. So if you already know about it, then bear with me. So exoplanets in general come into big categories. There are also objects in between these two categories, giant planets, think Jupiter. They're expected to have nearly, not necessarily exactly, but nearly the same composition as a star, mostly hydrogen, mostly helium, with a rocky core. Not necessarily, it's not clear, even for Jupiter, the exact extent of the rocky core. So think of basically the same material as for the star. I'll be discussing one giant object, a few giant objects we've been studying with SPIRO. You have a nice picture, and I really love this picture of, you'll recognize Saturn from a view that you cannot see from the Earth, where you see both the sunlit hemisphere at optical wavelength. It was a picture taken with Cassini, the Cassini probe, and coded in red here is infrared light. So giant planets and have thermal emission. So some of it is re-radiation of basically the light they receive from the star, but some of it comes from their own formation, their own contraction 4 billion years ago. So you don't, when you read about introductory stuff on planets in general, you say, oh, stars emit their own lights, planets don't, they reflect light. It's true, yeah, okay, it's true for amateur astronomers, but when you get into the details, you realize that giant planets in particular emit quite a bit of light that's left over from their formation billions of years ago. So here's an interesting emission from Saturn. Then you have terrestrial planets. They're mostly Earth-like in terms of structure, we think. There's not much atmosphere in mass fraction. You could say, well, that's rubbish. Venus is full of, that's a very thick atmosphere, but you just put that in mass fraction. No, it's very small, contrary to giant planets where gas occupies most of the mass. There's little water. You could say, no, oh, the Earth is full of water. No, just do the math in terms of mass ratio. Is very little. If you compare to the giant satellites of Jupiter, for example, you have water consists of there's a fair fraction up to most of the mass can be from water. So it's small, there's a small contribution to the mass budget. And maybe, really just maybe, and that's always a stretch that people tend to do when they present their new discoveries, they may be habitable to life as we know it. And there are things we know that are required, presence of water, but there are probably things that we do not know about that makes a planet habitable. Plate tectonics, do you really need plate tectonics to make planet habitable? That's unknown. So and that's one of the big research avenues, and I'll mention some work we do to find these terrestrial planets. And exoplanets, just think of basically, it's any planet that orbits a star other than the sun. So it's outside of our own solar system. So we all live on a nice exoplanet as seen from aliens. So if you were looking at the Earth from outside, it is an exoplanet. So it's, yeah. And they're all around in science fiction, but not only, of course, they are also found in studied. So just think of planets. 10 bonus points to the student that can name these planets, and be careful, there's a trap. So who volunteers?
The planet in the middle is Tatooine, and the one on the right, that was in Star Wars Episode 2. That was called Camino.
Oh, you're too good. Hey, that's 100 points. I didn't say that. Okay, but there's really a trap for the one on the left. I want the planet's name.
Planet's name.
What is it?
It wasn't Tatooine?
No, that's Tatooine. The one on the left.
Oh, the one on the far left.
Was that?
I don't recall the one on the far left.
Okay, it's Pandora, but Pandora is the moon. The Pandora is an exomoon. I can't remember it myself, so I'll have to check, actually get out of the slides and check my notes, because it's, the giant planets is Polyphemus. Okay, so that was a trap. There's always a trap in an exam. Okay, anyway, back to the slides. So yeah, so we have never, we don't have yet a solid confirmation of an exomoon such as Pandora. By the way, if you know, there are some tantalizing hints of exomoons. They must exist. There's no good reasons for exomoons not to exist, but they're already, planets are hard to find. Finding an exomoon is hard. We should at some point find one. There's no reason, but they're hard. So wait for Pandora. It's not done yet. So there are lots of questions. So our own solar system hosts 8 or 9 planets. Obviously, don't get me started with Pluto. Are there other types of exoplanets? So having just 8 or 9 of a sample is not, it's not a great sample. Are there types that we do not know of within our solar system, how diverse they are? And you want to put planets into categories, looking for, well, to understand the as populations. So having 8 planets that you know well is not enough. Where do they fall in population? Do you have planets that look alike, but that are not basically near twins? Do we have unknown types of planets? Do we have planets that we thought should exist, but they don't, that from models, that the gaps? I won't get into that, but there's, for example, there are very few planets that are twice the size of the Earth. You get planets more massive or less massive, and then there are physical good reasons for that, but you generally do not find planets that's twice the size of the Earth in radius. Just one example of a planet, not saying that they don't exist, that they're rare. And it just sneak preview on what's done. Basically, it comes from the fact that either you're below and you don't accrete much gas, or you're above and you pass a threshold and you accrete a lot of gas. So there are planets that you think intuitively, yeah, well, you should find a planet twice the size of the Earth in radius, but they're rare. So that's an example of a planet that does not, well, not saying that they don't exist, but they're rare. And you can find weirdos, and I'll show you one of the weirdos. That's my weirdo planet. So alien life, one of the big questions, and I won't answer that one fully, of course. What makes a planet habitable? Where are they in terms of orbits, in terms of host stars? Are they inhabited? Can you probe their atmospheres? And I'll show you the beginning of the long story to get basically this answer. Can we probe the upper atmosphere of these planets to see if there are signatures of life? Life as we know it, there's always, when you talk about life on exoplanets, someone saying, hey, could you have life with silicon or other materials? Or, okay, we talk about life as we know it because you would not even be able to recognize it if it were any different. So yeah, I know it's naive, but you have to start somewhere. That's just a very pragmatic answer. So life as we know it. Don't think of little green men yet. We may be seeing lichen or viruses, coronaviruses, maybe no, maybe not, or jellyfish. So when we say life, and ultimately around these worlds, is there intelligent life? Well, that's not the topic of this talk. Okay. So in general, you want to find exoplanets. You have to fight against 3 big ratios. Put it the way you want. It's either a problem of flux ratio. Exoplanets are very faint in the infrared. As I said, massive planets do emit light in the infrared. It's either a factor of 1,000,000. If you want to see a planet next to its star, invisible light, it's a factor of 1 billion. And I admit I had to Google it, okay? But the flux ratio between a dragonfly, another firefly, and the lighthouse is 70 million. If that's a good trivia question. Well, that's not even quite the ratio between an Earth and its sun. Okay, so that gives you an idea of the challenge of seeing these planets. It's the ratio in the infrared for massive planets is basically it's easier, but yeah, for an Earth-like planet around the sun, it's a factor of 1 billion, and you're not there even yet with the firefly. If you look at radius, if you think you've probably heard of transits, and I'll discuss transits, it's a ratio of 10 to 100. So factor of 10, it's not that bad, but what you see is an area ratio. It gets worse. Of course, if you have a disk that's 1/10 of the radius, it's 1/100th of the area. So you have to see something passing in front of the star. That's a factor of 100, not that bad, or 10,000. Yeah, it's that bad in ratio. Or you could go for mass ratio, and that's what we do with the radial velocity technique that I'll discuss, and that's SPIRO. It's a machine that measures the radial velocity of the star. You see a dynamical effect, but you're fighting against a mass ratio of a factor of, at best, around 1,000. So that's a groundhog relative to an elephant. And or up to for the Earth around the sun, and we're unable to find a planet such as the Earth around the sun with any instrument, but we think we may get there at some point. It's a chipping sparrow around an elephant, though I know that they don't live in the same place, but just bear with me. That's just, so that's a factor of 100,000. So you have to see the dynamical effect of that little bird on the elephant, basically, to find the exoplanet. So I'll get to SPIRO, next slide, but just as of now, we have more than 5,000 planets confirmed around other stars. There are that's literally more than 1,000 papers a year. Okay, so it's really an exploding field. It's more than 9 per work day. If you include all contributions, not just a peer review, but all contributions. So it's more than one. So basically you could probably spend all your time, work time, just reading papers on exoplanets just to see how active it is. Shortest period is 5 hours. So that's not the rotation of the planet, it's the orbit around the star. The longest one is more than 100,000 years. It's found by a former IREX student, Marie Evenot, by the way. Okay, there may be other planets that are longer than that, but just I had to say, hey, we have some former student that found that. And with temperatures going up to basically the surface temperature of some planets being hotter than some stars themselves. And you'd think that terrestrial planets and Earth-like, let's say Venus or Earth-sized planets, well, we have 2 in our solar system, 3 if you count Mars and so on. There's one system that has at least 7 of them that's known. So you think that we have lots of planets locally, but no, some stars do better than our sun. And you have dedicated space mission. I'll come to that. So the method, so wait, not too fast. The method I'll be discussing in this for SPIRO, and it needs some context, is the radial velocity method. So we're looking at the dynamical effects of planets on their star with SPIRO. Well, so that's one of the things we do with it. And this dynamical effect, think of the groundhog around the elephant. Well, one orbits the other. We always say, oh, the Earth goes around the sun, and I'm not a flat earther, by the way. The Earth goes around the sun. It's true at 99.9%, but to be more accurate, they both orbit a common center of mass, and you see the motion of the star. So here's basically your planet, a star, the spectrum you see, and as you don't see the planet, but you see the wiggle of stellar lines as the planet orbits. So the star comes toward you. No, it comes when it comes toward you, you have a push toward the blue. When it goes away from you, you have a push toward the red, and you can measure that with a spectrograph, and that's what we do with SPIRO. So SPIRO is an instrument that does exactly that, measure radial velocities. It can measure all sorts of things. I'll go to other things it does also. And it does it in the infrared domain for all sorts of reasons. One of them being that the stars are less active in the infrared. Also that you have access to other chemical species that you do not get in the optical. So just as a side note, I guess you're not too familiar with Belgian comics. SPIRO is this character, and there's a little SPIRO, okay? And it's basically famous in France and Belgium and Quebec. And it spells a spectropolarimetre infrarouge in French, infrared spectropolarimeter. I guess you probably guessed that one. And yes, in case anyone asks, yes, we asked the editors, and that's also why we had some drawers from the some people that do the drawings for the comics that basically did comics for us on the instrument, which is pretty cool. So SPIRO, it's a project that was started, oh my God, 13 years ago. That sounds really far. It was initially funded by the Canada-France-Hawaii Telescope, then dropped, then financed by Canada's Foundation for Innovation institution also in France, funded it. So it had a pretty rough start. Its construction started in 2015. We delivered it in 2017 to Hawaii, and first observation in 2018. So we've been operating it for a little more than 3 years. We were allocated as a team, the SPIRO team, more than 200 nights to study exoplanets. And it's ending, that first allocation ends basically next year, and we'll, of course, go for more telescope time. So we have teams from Taiwan, from various institutions in France, Switzerland, Quebec, Victoria, Brazil, and it all goes to Hawaii in the end. So the people at the University of Hawaii also that get some observing time on SPIRO. How does it work? It is, well, you have a telescope, a fiber, and a big optical instrument. I'll get into how they work. So basically, a telescope is just a big bucket that gathers light. You have to do something with that light. It gets injected in a fiber. I had to check, and it's 40 meters. So I thought, okay, maybe express it in feet. And there's a scrambling and then an optical instrument that decomposes the light. I'll show you what goes inside. So remember, telescope injects into a fiber, gets into the fiber into a vacuum tank. So get a little bit more specific. You get into this big vacuum tank. It looks like a propane tank behind a restaurant. It's about 3 meters long. So you arrive from the telescope, go into parabola, go into prisms, a grating, back into the prisms, back to the parabola, back to a fold mirror, back to the parabola 3 times, and then through a camera, and then onto an infrared array. It's the biggest infrared array that's available. Basically, maybe the military have bigger ones. It's a 16 megapixel detector, which doesn't sound that bad, but it's for an instrument that can observe all the way to 2.5 micron. It's the biggest detector you can buy, basically. Here's a simple schematic of the instrument, again, in simple optical drawings. Basically, you have a lens, produce a pupil, go to dispersing elements here, back to a pupil, and then you have a camera and a nice image at the detector. That's how it works. And you want to measure motions on the science array, just to scare you, at the 1 part in 1,000th of a pixel, basically, scale. So here's I just wanted to show this slide. It's basically done by the people that do SPIRO at the Dupuis edition, basically showing, well, the actual mechanical details of stabilizing and so on. And there's even the PI of the instrument, Jean-François Donati here, that's illustrated by comics. Even Claire Moutou, also the resident astronomer at the Canada-France-Hawaii Telescope at the time. Anyway, so inside the beast, so you have the parabola that's hit 3 times here, all the dispersing elements, and the staff in Toulouse, France, that were basically assembling it. Here's again the instrument. I'm just showing these pictures because I find they're nice to show the instrument. So after years of construction, that's basically the champagne, it's not champagne, I guess, of the first light in 2018, where we have the first science data. There's a whole effort into analyzing and converting this science data that gets on the detector into actual usable velocities and so on. And myself, I helped assembling the camera of the instrument. So that was until 2018. And just when you think that everything goes fine and everything's okay, you receive one of these emails that they had in Hawaii in 2018. Just, you can check the date, just in May. So we had first light, like, I think the first light of the instrument, first observations done in April. So just a month after the first light, and less than a month, we had an enormous there was an enormous earthquake in Hawaii, not enormous, 6.9 on Richter scale that shake the instrument, an instrument that you want to be stable. It moved, and so it wrecked all the calibrations. It's the only big earthquake we had in the life of SPIRO yet. It did not damage anything, but that was an adventure. And I was in Hawaii close to that time, and we actually saw the big eruption, which was pretty cool. So SPIRO, the SPIRO observation are divided in 3 sub-surveys. As a blind, I say blind because we don't know in advance if there's an exoplanet there, a blind survey to search for exoplanets in stars within 30 light years, really close to us. An informed survey, so we know there's a star, a planet passing in front of its star, and we just follow it up. We want to know the mass of these planets. And transit spectroscopy survey, basically we know there's a planet transiting a star. We may know its mass in advance, and then we want to get into the chemistry of its atmosphere. The blind part, I won't show much result on the blind part because it's still ongoing. It's a long, you need to get the long sequences of observations. The goal of this part of the survey is really to prepare what's going to happen in 2035, and of course, maybe a little before, a little after that. We'd like to get direct images of Earth-like planets around nearby stars. We're unable yet, but we think we may be able within a decade or a little more. And so you need to find the planets. So surveys to get an image of the planets themselves, a little point next to its star, a factor of 1 billion fainter. We'll need to know where to look for these planets, because they'll need days and days of integration to see anything. So we need to find them in advance. And here's a sample of an observation that shows the detection of a planet that's about the size of the Earth, about the mass of the Earth, around Proxima Centauri. So it's the nearest star to us after the sun. And it's a little wiggle basically in the data. You can pass this. So that's the reflex motion of Proxima Centauri, a little more than a meter per second in amplitude. And that's what we have now on this planet. And that's what we'd like to see one day. We'll see a spot next to its star. So we're in the race to identify these Earth-sized planets. We are able to infirm, so we killed one. It's not published yet, so I won't say which star. We also so observing planets that are thought to be there. So we're also confirming things. Yeah. So that's one part of the survey, and it's really paving the way for telescopes such as the European Very Large Telescope. That's a telescope that's being built as we speak in Chile. It's a 39-meter telescope, and it's with a 30-meter telescope that may get built in Hawaii. They will be the first observatories with a decent chance of getting an image of an exoplanet in reflected light. I'd like to say that we really go for reflected light. So we have seen exoplanets orbiting their star. Here's a gorgeous sequence done by Christian Marois, Jason Wang, where you see 4 planets orbiting HR 8799 star, which is what we'd like to see, let's say with Mercury. Show it again because it's just so nice. So you have the star behind a mask here, and you see these 4 giant planets. They're bigger than Jupiter, but we'd like to see the same thing for, let's say, Mercury, Venus, Earth, and Mars, let's say. Okay, again, because I like it too much, it's a system of 4 planets that are about 8 to 10 times more massive than Jupiter, and here they are in thermal emission, not reflected light. So it's really planets that are still emitting light from their own contraction. And what we'll hopefully see in 2035 is something like this, where you have a cube, where you have position in the field, and you see through all sorts of correlation techniques. And I don't want to get into that, but we'll be careful when an astronomer says, hey, we'll see something. We'll see that. We'll say, and we'll ask an artist to draw a little map like that and say, wait, we've seen that. No. What we'll see is probably a correlation in a map. So with a position in the sky saying there in the image, there is something that bears, let's say, methane in its atmosphere. Okay. So when I say image, you take it with a grain of salt. So yeah, we'll say that's what you'll see in the press release, that what the astronomers will publish basically. So that's the blind part of the survey. So now there's the inform our researchers. So we basically follow up on things that are known to be there. So there's a fantastic mission, NASA mission, the TESS satellite, that's scanning the entire sky. It looks at the big ribbon that's about 1/24 of the sky at the time, and basically doesn't blink and just stays there. and monitors the brightness of all stars. And it sees little things passing in front of the stars just by having little dips in the light curve. It has been running for 2 years and a little bit, and it's incredibly successful. It's all the data is public. So yes, if you really know what you do, you can just with a good internet connection and a comfy couch, because it takes some time, find planets from home. But yeah, it requires some work, but it's all available. So all teams just rush on the data when it comes for a new sector. Here's TOI 1278. It's a system I worked on. It's a paper I published earlier this year, where you have the test light curve. So flux, 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 and a little dip, and flat, 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 and a little dip again. So there's this TOI 1278. It's an M dwarf. So it's a star about half the mass and half the radius also of the sun, that has something passing in front of it. So we follow it up with SPIRO. So it's on an 18-day orbit, and there's not much else happening with that star. Oops, wait. Yeah, okay. So the TOI 1278, the big surprise is the enormous radial velocity signal we measured. So if a Neptune mass planet would have had about a 10 meter per second signal. So the signal that we get, the pull and the push from the kinematics, is basically kilometer per second. So it's a huge signal. And it's this object that's really an oddball, because it's an object that's 18 times more massive than Jupiter, but it's around a star that's half the mass of the sun. And that's really weird, because it's way too massive to be a planet as we understand it, but it is not a binary star, because binary stars tend to have, especially for low mass stars, tend to have a mass ratio that's close to 1. So it's odd. And if you put it in a host star mass, so it's half a solar mass thereabout, versus planet or companion mass, you have some brown dwarfs on really distant orbit that are known, but it's the first time we find anything like that that's that close. So 18-day orbit, where you would think, yeah, but it's something that should form within a disk, as you form planets in protoplanetary disk, but it's just way too massive to be formed in a disk. And yeah, it's odd. It's hard to explain actually how it got there. It's obvious in the data, but it's one of these funny oddballs. So yeah, my paper does not explain how it got there. We just say it's there, basically. Another really interesting system we studied with SPIRO was the AU-MIC system. It's a young star, so it's 2 papers, and it generated a flurry of papers. AU-MIC is one of the youngest nearby stars. It's a star that's 22 million years old, and it's a great. There are 2 planets, but I'll just discuss one, that have been found. And having a really young star with a transiting planet is nice, because it gives you an opportunity to measure both the mass and the radius, and hence the evolution in time of a planet. So basically, our planets at 22 million years have properties that are similar to planets that are 1 billion years old. And so finding a planet around a young star is really exciting for that, because it puts basically a point on the evolution tracks of planets. And here's the test light curve. So flux time, so that's 10 days and so on. And it's super messy. Okay, if you see that, you'd be okay. There are orange lines that guide your eye, but you have, first of it, you have like big, nearly but not quite periodic signal. That's basically spots on the star, and they're annoying if you want to find planets as they pass, because they mimic this variability. Basically, makes it harder to find transits, but it's also annoying when you look at the radial velocity, because you have spots and they induce all sorts of funny signals. You have that. You have flares, solar flares, but that's the same thing. Young stars have a lot of flares. And if you're really careful, you see that there's a little dip here, and there's a little dip there, and another one there, and there's a second planet. I won't get into that, but yeah. So there's a planet around that star, and you'd be really good at finding it. But so people found these transits, And with SPIRO, we observed it a lot, and we were able to reconstruct a map of these spots, basically the spots that produce this variability, this up, down, up, down. We've been able to see it basically in flux. So you have a polar projection of the star. So here's the Earth, polar projected. Here's the star, polar projected. I know it's an ugly map. It's a map of a star. When you think of it, it's pretty, I find it impressive. And basically, we use also the Z-man effect, which you've probably seen in your classes in atomic physics. Basically, the splitting of levels between of lines from magnetic fields. So we use a SPIRO, the polarimetric part of it, to measure basically magnetic fields and infer properties on what's happening on the star, and model basically the velocity of the star. So you see spots, you know how they will mess your radial velocity data. You can subtract that effect, and what you see under it, we see the planet. So here's the very messy radial velocity, but we're able to reconstruct a map, subtract it, and get this, and get the planet. And this sinusoidal line is informed also by the transit. So we know the period. So the period here is not arbitrary. We know it from basically these little dips in the light curve. So 10 bonus points to anyone that knows the solar system age. So 22 million years. How old is the solar system? Anyone knows? No?
4.9 billion.
4.5?
I think I read somewhere 4.9 billion, and I heard that number for something else.
I have to check because I noted it, but it's 4.571. And no one will get the points. So it's, yeah, so it's a system that is basically a factor of you can do the math in your head, to a factor of 200 times or younger than our own sun, and it has a planet. So when you look at EUMIC, so now we have a mass because we've seen, we've seen the reflex motion of its star. We have its radius because we've seen the little dip. If we have a radius and a mass, we have a density, and we can compare the planetary radius, planetary mass with tracks with known planets. So the little blue points are known planets, and basically the planet falls within the bulk of known planets. It's this orange point here. So it means that a planet that is comparable to Uranus, Neptune is formed more or less, has its density, matches the bulk of the distribution. Not saying that it won't contract anymore. It could go further down, but it's not way up in properties. So we knew its radius from its transit, but it's not, let's say, an Earth mass planet that would be super puffed up and still undergoing basically an enormous puff of gas. It is a planet that has properties that match the bulk of the population, which is already interesting. It adds a point saying, well, yeah, planets can be within the bulk of the population of objects that are mostly a billion years old. Even at 20 million years, they can be there already. So which is interesting in itself. The last part of the SPIRO project, surveys is the transit spectroscopy. So we probe planetary atmospheres. Basically, you have a planet passing in front of its star. You can probe the planet's atmosphere and hence its habitability. Do you have properties in the atmosphere that are allow for life? Okay, we're not doing a life with SPIRO, I reassure you, but that's the ultimate goal. So you have a planet that passes in front of its star. If there's a wavelength where the atmosphere is more opaque, let's say water absorption, the planet seems bigger. If there's this, if it's more transparent, let's say you take the Earth in the optical wavelengths, basically 500 nanometers, the atmosphere is reasonably transparent. So the Earth would seem smaller projected against against the star. And it's that tiny difference, not in the dip that you get from the light curve. It's a difference in the depth of that dip that you can measure, and that informs you on the chemistry of the mostly upper atmosphere of the planet. You would not go with the Earth down to the ground. Let's say you'd get the upper atmosphere. Do you recognize this star and this planet? That's a little quiz for you. I love little quizzes. Who's that?
Venus.
Hey, it's Venus. It's actually a ground-based image. It's an incredible image of Venus transiting the sun. I don't remember if it's the 2004 or 2012 transit, but it's Venus passing in front of the sun. And you see a tiny, tiny limb here. It's refracted light from the atmosphere of Venus. And Venus has a beefy atmosphere. And that's about the scale height you're talking about for this atmosphere. Okay, it's not the same physical process because you'd be looking here. You see the mouse? You'd be looking here at difference in radius, but it's a tiny effect, okay? We're not there yet for Venus around us. So a Venus-like around a sun-like star, we're not there yet. I reassure you, but that's the ultimate goal. If you take a planet that you know even better, its radius, the Earth's radius would be about 6,371 kilometers in visible light and about 20 kilometers bigger if you look at 1.4 micron where there's a deep absorption band. So imagine that 20 kilometer here, let's pretend it's the Earth, that 20 kilometer makes a bigger dip in the light curve, and you can use that to infer properties of the planet. So we did it with SPIRO on a much easier object than an Earth around the sun. It's a hot Jupiter. So it's a planet that is about the size and mass of Jupiter. It's orbiting a star slightly smaller than the sun, not much. And it's very hot, which puffs up the atmosphere, which helps basically measurements. And that's thesis work from Anne Boucher. There's another Anne doing astronomy that's from Quebec. Basically, she was able not to measure the spectrum, but see how, imagine this as basically the sum of all the water lines in the spectrum of the planet. So it's what's called a correlation function, but you can imagine we know from molecular, from textbooks, we know where water line absorption should be. And what she did, and it's a standard procedure, is you just stack up every single line that you see in your spectrum into a mean line, and in a sense, that's this mean line, and she basically detected water. Okay, it's not detected the water on an Earth that says that there are oceans. Of course, it's a planet that's similar to Jupiter, that's very hot. But from that work, she was able to measure, I think, winds. She was able to measure a profile, constrain the profile of the atmosphere, have an idea of the cloud deck altitude, and basically, unsurprising, it is hotter at the bottom, about 750, and cooler higher up in the atmosphere, which is pretty typical. There's a cloud deck at about the pressure of 1 bar, and she was able to measure a 30 part per million water abundance, which is super dry by any Earth standard, but it's still pretty impressive that we can do these measurements on objects that are admittedly way more favorable than on Earth, but it's the beginning of it. Just a side note, it could be the topic of 10 talks in a row. There's an instrument aboard the JWST space telescope. It's the telescope that's funded by NASA, by European Space Agency and Canadian Space Agency. And as I'm giving this talk from Canada, I'll mention the NIRISS instrument that's aboard it. That's one of the 4 instruments. There's part of it is the guider, but there's also part that does spectroscopy. And there's an instrument, this one, that's really tailored to do transit spectroscopy of exoplanets. It will not do it at very high dispersion as we do with SPIRO. It does it at low resolution. So it's designed to see changes, bulk changes in the shape of the spectra during transit. And it gives you different information. So you will not get a mean line as we got with Anne's thesis work. You'll get basically broad molecular bands. It's complementary, and we will have overlapping samples. So our team has 250 hours of guaranteed time. When you build an instrument, you have guaranteed time on JWST. We'll do a detailed atmospheric, get the detailed atmospheric composition, mostly of the broad shapes of the molecular bands. You're sensitive to clouds. You may be more sensitive to problems. I won't get into that from the star itself. In parallel, we'll have a survey with SPIRO also another instrument. I won't discuss this instrument, but that's similar to SPIRO that we're building for Chile. It's underground. One major thing is that you can send a technician with a wrench to fix it when things go wrong. It's harder in space. We'll have more than 10,000 hours of guaranteed time. We can measure winds and do things similar to what Anne did for her thesis. So if all goes well, that's an observation of an Earth-like planet. We'll get on an Earth-like planet around a nearby M dwarf, we'll get correlation functions like that, and basically broad structures in the spectra that inform you on presence of water and maybe biosignatures. So we'll say that we see something like this, but that's what we really meant, actually. And that's it for the talk. And just as a slide, that's an unashamed advertising for grad studies in Montreal if you want to consider going to do this. Is, I think, the most exciting time ever, and I really mean it, ever, to study exoplanets. We were past the first few discoveries. We'll say, okay, there are things there. We're really getting into the meat of the science, I think. So yeah, we have a great team in Montreal. Montreal Bishops is not Montreal, but it's close to Sherbrooke. We have grad students, postdoc staff from France, Iran, and even Americans, yes, and they're happy, from California and Maryland. So yeah, do consider coming to Montreal if you want to study exoplanets for grad school. It's not that scary. And the Bishop and McGill are English-speaking universities. Well, we have some even more courageous that come to EDM. You can write your dissertation in English, though the grad student life is mostly in French, but they survive, they're happy, I think. And it's only a little less than 6 hours drive from your place, so it's not that bad. And we exist on social media, and I'm not in charge of social media for good reasons. And because I would be terrible. So we have, basically, you can follow our team adventures, basically here. I could send the link if you want. Questions? I barely hear you. Ooh. Can hear you.
In one of your slides, you mentioned xenon splitting being something that you're observing. Are you observing that due to the magnetic field around the star, or?
Yep. It's the star. Okay, that's worth a little explanation. What's really annoying from an active region on a star is that, imagine you see my hands, like the star rotates, okay, and a spot on it will induce a jitter in the radial velocity. So you want to know the distribution on spot on your star, but star spots have strong magnetic fields, so you can see them through Zeeman splitting, because the Zeeman splitting also yeah. So basically you see the polarization effects from the spot on the star, not the planet itself. So I'm more into the radial velocity aspect. It's more the team in Toulouse that does the work on Zeeman splitting. But yeah, it's really the magnetic field within active regions that you monitor. Yeah.
Thank you.
Other questions?
Hi, I'm interested in the blind survey. Can you remind me how many stars there are out to 30 light years? What is the sample that you're looking at? And how
it's 10 parsec. Okay, it's the 10 parsec. There are about 300 stars within 10 parsecs, but we focus on about 50 of them. There's a list of reasons why you would reject a star, like too tight of a binary, then the system's not stable, and it leads to problems. It has to be seen from Mauna Kea. You don't want it to be too active, and yeah. So yeah.
Are you expecting virtually all of those stars to have planets? What's your expected yield?
To M dwarfs, you expect basically most of them, at least a majority of them, to have planets. There's a correlation between the most massive planet and the host star's mass. So the lighter the star, the lighter the planets. Okay, but M dwarfs tend to have lots of Earth-like planets. That doesn't mean that we're able to find all of them. That there are geometric effects. If you see the system pull on like that, it doesn't work. You see no RV effect. Yeah, but
That's pretty rare. You expect most of them to be in some considerable angle.
yeah, it's relatively rare. If you take random spheres and just throw them in space, it's pretty rare that you're in a really different role. In the really bad case of being pole on, it happens obviously, but it's rare. But yeah, it's still ongoing. We are actually killing more planets than we're finding, which is good for science. But yeah, there are some that we're able to show that it's due to activity, for example, misinterpretation of activity, which is good for science. But it's a joke I make. It's like in my career, I want to kill more planets than I discover. So that's we'll see. Yeah.
I'm also curious about the brown dwarf himself.
What's the
brown dwarf? I was surprised at how weak and short and small the transit was. I would expect these two objects to be basically the same size, right?
Well, yes, and there are two things. It is a grazing transit. So okay, it's a 1% deep transit. If you take the radius ratio, you'd expect about a 4% deep transit.
Oh, that's all. Okay.
That's all. Okay, there's something funny with very low mass. So this star is half a solar mass, which is kind of on the heavy side of M dwarfs. But if you go to the really coldest stars, they are indeed the size of brown dwarfs. It's a tenth of a solar radius, and for stars and brown dwarfs all the way to Jupiter. So if you take M8, M9, the coldest red dwarfs, they are the same size as Jupiter. But here we're really at the M0, so it's nearly a K dwarf. So it's about half. So it's about 5 times bigger in radius. So it's a factor of 25 in area. That object is about a Jupiter radii, so it's 25 to 1. So that's about 4%. That would be a full-on transit, but it's grazing. So it's basically touching the pole of the star. So we had a big ambiguity on the actual size of the planet or brown dwarf. So it could have been significantly smaller. So that was ambiguous. So that it was not followed by other teams. And we were quite glad because, okay, maybe it's a Saturn size, a Saturn mass, and so on. So we follow it up, and we discovered it's really an oddball. Yeah.
Thanks.
I have one question.
Oui, yeah.
Exoplanets themselves. Is there any studies with your group SPIRO that actually looks at the property of the star itself and how it could impact the life on those planets, like activity and stuff like that? I've seen some for other type of telescopes. I've seen a lot of that kind of proposal.
There are all sorts of aspects. So, okay, there's one thesis. There's one grad student. He's doing his thesis on chemistry of M dwarfs. Okay. Not just bulk. I don't know if grad students, undergrads are familiar. We say just metallicity. It's anything that's heavier than helium. No. He goes in the details. You have more titanium than iron, than oxygen, and so on. So it's surprisingly so detailed studies like that. There have been a few, obviously, but yeah, he really goes into the detail of the chemical abundances. So he started with Barnard star, which is an interesting object because it's relatively metal poor, and he will expand it to the entire SPIRO sample. That's one thing. How does it impact the properties basically, and how the ability of the star and the system to host life? That's still TBD. And you may have interesting correlation that go the wrong way, because you could think that system that host planets may have chemical properties that differ from systems that do not host planets for basically star formation reasons. Yeah. Oh, wait. So yeah. So it's being done, but the bridge toward habitability is not done yet. M dwarfs, so red dwarfs, have been, some people argue that they are bad for life because of flares. because you tend to have higher UV flux from flaring, what you see in the UMIC. It's being debated. I've seen, so it's really early in the life of the system. So if you have water that comes later on or outgassing from the planet, it may be habitable and comparable to what the Earth receives in some cases. So it's anyone's guess. Yeah. Questions about, yeah.
That sometimes planets will be a different size based on their atmosphere is made of. Are there any ways to like differentiate, like if a star looks bigger to a different atmosphere, or if it actually is bigger, or like planet a star?
I didn't get. Yeah, could you repeat closer to the mic, or someone could repeat?
You had mentioned that a planet might look to be a different size based on what its atmosphere is made of. Are there any like ways that you guys can tell if it is looking bigger because of a certain atmosphere, or if it actually is bigger?
It's okay. Yeah, but well, it's actually an interesting question because the difference in radius from the atmosphere is tiny compared to the bulk of the bulk of the radius of the planet. Usually, not always, but usually. So you're not wrong. You're not wrong with the bulk properties. That's the density of the planet. If you take higher up or lower down in the atmosphere, you're not that far off. But it does raise a good question about there's an ambiguity that comes close to what you say. It's if you have clouds, okay, you could miss part of the atmosphere, and there's nothing tells you that the atmosphere doesn't go deeper, but there's just a layer of clouds that's preventing you from seeing below that. So there's no true like zero radius that you can get. So that there is an ambiguity relative to where's that kind of zero radius that you see. And in most cases, if you even the Earth, you'd see the Earth in transit, you probably would not be able to get the actual rock layer basically of the radius. You'd probably miss it by about 8 kilometers. So there's an ambiguity on what's the ground basically. But for now, we're mostly looking at Jupiter-like planets, so there's no ground, so it's okay. But it's true that we will not get to the actual zero like rock basically in terms of radius. And there's an ambiguity there. Yeah.
Maybe sometimes something that can help you is the lines that you are looking in the infrared. They are signature of gases. So it's not the surface of the planet, right? So they can tell that's coming from the atmosphere and not the surface of the planet itself. Unless you are, I'm guessing, dealing with gaseous planets. So then how do you define what is the planet and what the atmosphere is? So that's another question.
But it's true that there's, if you take a hot Jupiter, you take your entire domain, you look from 1 micron to 2.5, you see deeper or higher up, but there's nothing tells you that the deepest line you see is actually a ground. No, it's just thicker layers of gas. And so there's no bottom yet. On a super thin atmosphere, you may have a kind of a flat bottom, but we're not there. Especially objects like such as the one that Anne Boucher did for her thesis. They're big hot Jupiters, so they don't have a rock layer. But it's an ambiguity. What's that zero floor there?
More work for you.
That's a good topic for a thesis, just say.
Time for one more question, if any. We're 1 minute past 5, so let's thank Etienne.
It's a pleasure.
Etienne, merci.
C'est un plaisir, hein?
Ça fait longtemps que je t'ai répondu.
Passez nous voir, hein? Tu sais connais l'adresse à Montréal.
Les étudiants attendent pour aller chercher leur snack.
Bon, allez, have a good snack. Oh, there's food. Good. Bye-bye.